Okay. Good morning, everyone. How did the homework go? How did the assignment go? Do you have any questions about the homework? Please get going.
Could you do C on either one of them? I just want to make sure I got it right. I'm not 100% sure.
C. Okay. Any other question? You guys can put them on chat. So number C. Okay. So, all right, we'll do the first one. And so, okay, we'll do the second since it doesn't matter. Since another of your classmates asked for the second, we will do that. And I will answer C in both of them. So we have the following function, f of x equal x squared minus 3x. Okay. And my first question is, we have to estimate integral from 2 to 5 of x squared minus 3x dx. We have to estimate. And we have to estimate using Riemann sum. Now, I was not really precise about which one, which is my mistake. So we're going to use estimate, you're going to use the right sum. Riemann sum. And I want you to do it with six subdivisions. So let's do that. So my function, the function in question basically is this one. That's really the function is. What is the definition of the definite integral? It means, or what do I mean by estimate? Estimate, it means basically we want to graph it. We don't have to, but I will graph it. I'm going to graph the function f of x equal x squared minus 3x. So, so that's a parabola. It's 0 here at 0, and it's 0 when x equal to 3. So it should look something like that. That's my parabola, okay? And 2 should be somewhere in here, and 5 somewhere in here. Okay, so that's really, I'm estimating over the integral from 2 to 5. And I need to do 6 subdivision. It means I need to take the interval 2, 5 and divide into 6 pieces. So this is my interval of interest. I'm dividing into 6. So the delta x is going to be 5 minus 2 over 6, 3 over 6. It means a half. That's my delta x. So I need to divide it into, so 1, 2, and okay. These are my subdivisions. So let us see what they are. If this is 2, this is going to be 2.5 or 2.5 halves. 3, 7.5. And that's a 4. And that's a 4.5, which is 9 halves. Okay, so that's the subdivision. And now what is the sum? We're going to take the value at the right endpoint. So that's my right endpoint. We take the value of the function times the delta x, which is going to give me minus this area, plus the value at 3 times delta x, which happened to be 0. The value at 7.5 times delta x, which will give me positive this area. And then the same here, the same, and the same. So basically the Riemann sum is going to be with 6 subdivision minus this area below plus the sum of the area of those rectangles. Okay, so that's really the picture. Now we have to write the sum correctly. So the definite integral it's not going to be a great estimate because we don't have a lot of subdivision, but that's the idea. So x cubed minus 3x dx. It's almost equal to the value of the function at 5/2 times the delta x. This would give me minus the area of this little rectangle, plus the value of the function at 3 times the delta x. So I'm just writing it clearly for all of us, plus the value at 7/2 times the delta x, plus the value at 4 times the delta x, plus the value at 9/2 times the delta x, plus finally the value at 5 times delta x. Okay. So that's really, we are writing it clearly. That's what my question is. So it's equal to what? What is the value of the function at 5/2? So let us see what the function is. The function is x squared minus 3x. So it means here I should have x squared, it means 5/2 to the power 2 minus 3 times 5/2. That's the value of the function here, times my delta x. This number is going to be negative because this number is the value of the function at 5/2. This is going to be negative. Multiplied by a half, the half is here. That's the delta x. That's my half. That's my delta x. That's my delta x. It's going to give me minus this area. Plus the value of the function at 3, if I plug in 3 here, I'm going to get 3 squared, minus 3 times 3, which is the 0, times a half. And then I keep repeating the same thing. 7 squared minus 3 times 7/2 times a half, and so on and so forth. So that's 4 squared minus 3 times 4 times a half plus. So it's tedious, of course. That's why I gave you a website to get those answers from. But that's how we do it. Plus finally, at 5, I will have 5 squared minus 3 times the 5 times a half. Okay? So that's really the sum. Now we compute this number at the end. That's really a calculator work. And we compute this number. Did anybody do the computation? Anybody did the computation? So I want to do the 6 subdivision. I'm just actually pulling the answer from.
Which one did you do, right or left?
I did right. I did right.
Okay. I had gotten 10.625.
So I did the right. We're gonna get that much. I just checked it out by using the website I gave you. Okay. All right. Now my second question was, and then finally part C, and we finalized. Part B is we have to estimate using Riemann sum with 100 subdivision and 200 subdivision. And of course, I'm not expecting you to do that. I gave you the website to use. Okay, so if I take more subdivision, basically I take this piece and I divide it into more, a lot of pieces. And I do the same thing, a lot of pieces. Okay, and the definite integral is what happens when we take more and more subdivision. I mean, so if we do that, if I take 100 pieces and I basically just get the numbers, so part B, if I take 100 pieces, then the Riemann sum was 100 pieces. And now I'm going to totally pull it out from the website I gave you. So I will share the screen. Sorry. Write Riemann sum equal, it's the integral, which is the estimate, equal. Okay, so I'll share the screen with you and we get the answer. Which one I want? I want this one. All right, that's the screen, that's the one we're using. That's my function, x squared minus 3x. X goes from 2 to 5, and let us do it with 100 subdivision. And let's see what it does for me. Okay, so basically they are very little. So what we are doing is, as I said several times, it's minus the area of this piece below plus the area of the piece above it. And you can see how well we're filling the area. So according to this, we're going to get the estimate, the R100 is 7.68045. That's really with 200 subdivision. Now, if I take 100, if I take 200 subdivision, and let us see what the Riemann sum will be. Again, we're filling up the region more and more this time, and this is giving me 7.590. So we're heading toward 7.5, so 7.68, 7.5, and we can keep taking more and more subdivisions, and as many as you want. As you realize, this can actually using, so if I take 2000 subdivision, let us say, okay, let's see what this gives me. I hope it can compute it, because the plot, it got stuck at 7,000, whatever. So it means that the integral itself should hover around 7.6, 7.5. So I don't know, 7.5 something. That's really, okay, here it is, 7.509. So it took it a little bit of time actually to compute. So when I took 2000 subdivisions, so there is 7.09. So the integral should hover around 7.5. And more subdivision, the closer we're gonna get to 7.5. Okay. Right. Now, part C. Part C is the following. I want you to write the integral as a limit of Riemann sum. So this is this situation. I wanted to learn the general format. So what is it as a limit of Riemann sum? What do I mean by that? It means in general, if I divide 2,5 into n subinterval, so this is the general format, into n pieces. Okay, so this is x1, sorry, this is x0, and this is xn, n subdivision, and I'm going to write the Riemann sum. So how would we write this? It's going to be equal to what? It's going to be sum, sigma, the value at x1 times the delta x, plus the value at x2 times the delta x, at x3 times the delta x, x4 times the delta x, and then at some point they become positive times the delta x. So it's going to be, first I'm going to write it the general format, and then I will substitute f by what it is. The value of the function at delta x xi times the delta x, I equal 1 to n, because the general Riemann sum, it means with n subdivision. And then the integral is what happened to the sum when n goes to infinity. So now in my context, what is f? It's the limit as n tends to infinity of the following sum. In my scenario, my f is this function right here. That's really what my f is. So f of xi, it means I'm taking the following sum. Xi squared minus 3xi times the delta x, where my I equal 1 to n, okay? Which is the same as, so when I tell you write it using Riemann sum, I expect this one, and I expect to write it in two ways, this and that. What does this tell me? It's the same thing, but here I'm gonna emphasize what is the delta x. The delta x every time is going to be the length of the interval divided by n. So the delta x is always the length, which is 5 minus 2 divided by n. And this is really what is my delta x is, which is 3 over n. Okay, so if I'm going to ask you, which is I will, because I want you to start seeing this, write the integral as a limit of Riemann sum, means I'm expecting you to write it this way and that way. I want both way of writing. Okay, that's really what I mean by that. Okay.
How did you get the I to equal 1?
Yeah, because, go ahead. Because when I take the right Riemann sum, so I'm using right Riemann sum. All right, when I take my interval, that's my interval, 2 to 5, because that's what I want. And I divide it into n pieces. Okay. And I'm going to label the endpoints. Okay, I'm going to give them labels. So how do I label them? This one I called x sub 0. Okay, this one x1. This x2. That's how I label those endpoints.
Okay, yeah, that makes sense. Thank you.
We have to label them, otherwise nothing makes sense. Okay, and we start here. So that's my x1, x2. But when I write in sigma notation, this will become my xi, 3 of xi.
I have a question.
Yes.
What does the second bracket, the first bracket mean? The first one?
This one?
Yes, the ones on the outside.
It's just the limit of the whole thing. It means you compute this sum, this whole sum, for n equal 100. Then you compute it for n equal 200. And then you compute it for n equal 1000. And then for n equal 1. That's what the limit is. It means you keep computing those sums for larger and larger n. It means for more and more subdivision. And the limit tells you, the limit means when n becomes very large, those sums are becoming close to what? That's really the idea. Okay, so the bracket here is just to make it, I mean, I don't have to write the bracket. I could have kept it like that. Okay, but I put the bracket just to emphasize that you're taking the limit of this quantity right there. So even if you don't put the bracket, it is correct.
All right, thank you.
It's just a way to emphasize is that's the sum that I care about. That's the sum I want to compute for larger and larger number of subdivision and see what's happening. So I do it for 100, for 200. And when those numbers become very close to one another, very, very close, that's really where I'm going to hit the actual value of the definite integral. Like 7.6, 7.5, those were still very far. So if I want to really find the value of the definite integral, I would have taken more subdivisions. That's why I took 2000 on the board and 3000. That's when I start realizing we're hovering around 7.5. But is it 7.5 or 7.6? Those are still not really clear. So I needed it. I went ahead and I computed 2000. And then I realized, no, I'm getting 7.5, not 7.59. So the idea of a limit, it means you compute the sum for larger and larger n. Any other questions? And the definite integral is exactly what you see. Exactly the sum is this. Any more questions before we move on to the last piece of the review? Okay. So since we're talking about Riemann sum and this sigma notation, let us say I give you the following. And so my question is, express, just by analogy, express the limit below, as a definite integral. So this is my limit. Suppose I take the limit as n tends to infinity of the following sum. Sigma I equal 1 to n of, suppose I put here 5xi plus, so 5xi squared plus 6 times delta x. So the bracket, only to emphasize, I'm taking the limit of this sum. And on the interval 1, 4, meaning what? Meaning that I'm taking the interval 1, 4, and I'm subdividing it into pieces, and I'm computing the limit of this sum. Okay, I want you to write this as a definite integral. So I want you to kind of see the analogy between this sum and a definite integral. So which integral really here I'm talking about?
Would it be the summa?
Yeah.
Go ahead, Christopher.
Go ahead, please.
Would it be the summa where that we use that little s thingy?
Integral.
Integral. Sorry about that.
No, you don't have to apologize. Okay. Integral. From where to where?
We put 1 on the bottom and 4 on the top.
Right. What's the function?
5x squared plus 6
5x squared plus 6
dx.
And our job now, starting tomorrow, we start going to be moving from here all the way to here. We're going to basically move backward. All right. So since now on, in this section, we're actually going to evaluate quantities, and we realize that this quantity will have this form. And then from this form, we're going to move backward into the definite integral. That's why I'm emphasizing this idea. All right, so now the last piece is the following piece, the fundamental theorem of calculus. Okay. So, which is not hard because I'm sure all of you now know that piece. So the fundamental theorem of calculus. So let us remember, I will never keep, hammering you with this idea that the definite integral is a limit of Riemann sum. So the definite integral is by definition these pieces, the limit of those sums, no more, no less. That's really what they are. Now, the fundamental theorem of calculus is just an extremely powerful rule, which allow us to evaluate those Riemann sums. So if I want to evaluate this, which is, as you realize, it's tedious. I mean, without this computer algebra system that I am using, finding R100 and R200, this is really a nightmare in the making. And historically, people had to do that to compute those sums. So till they discovered the fundamental theorem of calculus, which is, as I say, an extremely powerful tool to be able to evaluate those definite integrals. Means instead of doing those sums, we have a tool to do it. It doesn't work for every integral. It works for quite a bit of them. So it's a tool, it's not the definition. It's just a tool to help us do that. So what does it tell me? The fundamental theorem of calculus. Okay, it tells us the following. If f of x is a function defined on an interval AB, and big F of x is the antiderivative of f. So this is, f of x is the antiderivative of f, then to evaluate the integral from a to b of f of x dx is the value of the antiderivative at the upper limit minus the value of the antiderivative at the lower limit. Amazing theorem, absolutely, which was basically a revolution when it was discovered because it made calculus a bit easier to work with. So historically, people had to work with Riemann sum prior to discovering the theorem. And once they were able to discover the theorem, working with definite integral became much easier. And the discovery of the theorem is due to two people, Leibniz and Newton, the famous Newton. Okay, they were able basically to discover the theorem basically at the same time. And Newton is British, Leibniz is German, and for a long period of time, there were a big feud between supporters of Leibniz, supporters of Newton, on who actually discovered it first. But basically, they did discover it independently from each other, and they are both given credit for this discovery. And in sigma notation, in notation, sometimes f of b minus f of a, we write it as f of x with a line here from a to b. So what the fundamental theorem of calculus tells me, if I have a function, if I know the antiderivative, if I know it, then to evaluate the definite integral, we take the antiderivative at the upper minus the antiderivative at the lower. So the main requirement to be able to use the theorem is knowing antiderivative. Now, some functions, we're going to learn a lot about how to find those. Some functions, regardless of what we're going to learn, will not be able to find an antiderivative in an easy way. So for example, if I take the integral, let us say, of cosine x squared, it looks like very innocent, but it's not. Regardless how much we are going to learn how to find antiderivative, this function does not have an antiderivative that we can write it very easily. So it has this antiderivative is what we are going to call eventually at the end of the course is a power series. But there is no easy antiderivative for this function, regardless really how much we are going to learn. So the fundamental theorem tells me if I can find the antiderivative, I can compute the definite integral. Okay, and in particular, I like to remind you this is simple, but I'm going to ask you to give me the answer. In particular, suppose I'm integrating the derivative itself. Okay, this should give me what? This should give me what? I'll give you 30 seconds. What?
Just f of x.
Not f of x, because it's a definite integral, but you're on the right track. The antiderivative of f prime, it means what is the function whose derivative of f prime is f of x, but it's f of x between a and b. It means f of b minus f of a. So that's in particular. In particular, if the integrand is the derivative, then indefinite integral from a to b of f prime is f of b minus f of a. Watch f prime f. So basically the integral kind of cancels the effect of the derivative. So f prime is turned into f. Okay. So now the first problem I will do is basically I'm going to finish number 2. So in this problem, number 2, part C, we wrote the integral as a limit sum. We estimated it by using the Riemann sum. Now we're going to actually compute it using the fundamental theorem of calculus. So we're going to take back this problem and we're going to use the fundamental theorem to be able to evaluate one more time this integral, which should hover around 7.5 because that's exactly what the Riemann sum gave. So let's do that. So example. Let me take another page here. So it's crucial. This fundamental should be kind of totally drilled in your head. And so example. Use the fundamental theorem of calculus. And sometimes it's abbreviated fundamental theorem of calculus to evaluate integral from 2 to 5 of x squared minus 3x dx. Okay. So the first one, I will do it slowly, but then we will do it a little bit fast. So what does the theorem tells me? Theorem tells me if I know an antiderivative of this function, then I evaluate it at the upper minus the value at the lower, and I'm done. So the question really boils down to finding antiderivative. So let's find an antiderivative of that. So an antiderivative of f of x equal x squared minus 3x is f of x equal. So I'm looking for an antiderivative. Now we know that antiderivative of x squared is 1/3 x cubed minus 3 times antiderivative of x is 1/2 x squared. So plus c, of course. So this will give me 1/3 x cubed minus 3/2 x squared. So I said the first problem, I'll do it in a lot of details. Okay. So the fundamental theorem of calculus tells me the definite integral of my function is equal to the antiderivative evaluated between 2 and 5. Okay, what does this mean? It means you evaluate the antiderivative at the upper limit minus at the lower limit. So at the upper limit, it means I take the antiderivative and plug in 5 for x. 5 to the power 3, 5 squared plus c, minus 1/3, 2 to the power 3, 2 squared plus c. Okay. And now we're going to evaluate, and we should get around 7.5 because that's what the Riemann sum told us. Now 5 to the power 3, it's 5 times 5 times 5, so it's 125 over 3. 5 squared is 25, 3 times 25, that's 75/2 plus c, minus, now I need to distribute the minus, 1/3, minus minus, it's a plus, 3 times 4, 12, right, over 2 minus c. Okay, now that's very well. The c and the c cancel out. Remember, definite integral is a number. So we're not allowed to have c in the answer because it's a number. It's actually this net area. So we should not have c in the answer. So when we compute a definite integral, we have to find the antiderivative. But if we keep the c will always cancel out. So if you keep it, it will cancel out. So to make our life easier, when we find definite integral, don't worry about the c anymore. Because if you keep it, it's going to cancel out. So why to make your life a little bit harder? So you don't have to worry about the c. So whenever we have definite integral, we don't worry about the c in the antiderivative. Because if we keep it, it's all right. It will cancel out at the end. So make our life easier and let's not worry about it. So since now on, I will drop the c whenever I'm dealing with definite integral. Now the rest is I need to compute the sum the best possible way. 125 over 3 minus 8, that should give me, I think, 117 over 3. Minus 75 plus 12, so 75, so it's going to give me 63 over 2. And I can be extremely lazy here to the point of using a calculator, which is I barely use. Divided by 3 minus 63 divided by 2. And I will get, honest to goodness, 7.5, which is what the Riemann sum basically actually got me close to. Okay, so the Riemann sum almost gave me 7.5. The fundamental theorem of calculus is actually those Riemann sum, but when n is very large, when n is extremely, extremely large. Okay. And graphically, let's see what graphically this represents. What does 7.5 represent? It represents the following. I go back to my function. I never keep track, lose track of what I'm doing. My function was x squared minus 3x. When I graphed it for you, it looked like this. That's a parabola going up. That's my function. This is my 2. This was the 3, and this was the 5. Okay. So graphically, the integral from 2 to 5. of x squared minus 3x dx represent? We have here, up to here, the function is negative, and from here to here, the function is positive. So I'm going to call this region, let me call this region R1, or R if you want, and I'm going to call this region S. Okay. What does the integral represent? It represents equal. Who would like to tell me?
Is it S minus R?
S minus R, absolutely correct. Minus the, so let's call it area. Minus the area of the piece under the graph, it means minus the area of R plus the area of S. Okay, so it's not the area because the function here is taking positive and negative the value. Minus the area of the region below the x-axis plus the area of the region above the x-axis. So that's really graphically what this means. And this, the answer is 7.5. Okay. So I'm going to do one more problem along those lines, and then we're going to work with fundamental theorem of calculus with substitution. So here we are. One simple problem, simple problem. So let us say I want you to evaluate the following. Okay. Integral from 1 to 9, for example, of x minus 1 over the square root of x dx. Okay, so that's a definite integral. Remember, definite integral, the answer is a number, is not a function because it's in that area. So if you get, you have to get a number. So at this stage, I will ask you, if you're faced with this integral, how to compute it. Usually the basic idea is you have to find the antiderivative. That's really what it boils down to. And then do the evaluation. So how would you do it if you were me?
I would split it into two different fractions.
What?
I would split it into two different fractions.
Right, we're going to split it. So we have to split it. There is no substitution anywhere in the picture. So I'm going to do it x over the square root of x, right? That's what you mean, correct? Minus 1 over the whole thing dx. Okay. Now, of course, as I said a million times, I think I did, that integral does not work well with square root. So whenever you have square root, we have to write it as x to the power a half minus 1 over x to the power a half. So we're making it ready, basically. It's definitely not ready. Now I have still to use a little bit of algebra. X over x to the power a half is basically x to the power, if you want, 1 minus a half, the law of exponent. This is x to the half. So the first one is x to the half minus x to the minus a half dx. Now I have a difference between them. It's easy, so it's the integral. To find the antiderivative, I find the antiderivative of the first minus the antiderivative of the second. I can do that because it's a difference. I can split a difference. So the antiderivative of x to the half is 1 over a half plus 1, x to the half plus 1. So 1 over a half plus 1, x to the half plus 1 minus. Now I'm in the process of finding the antiderivative. 1 over minus a half plus 1, x to the minus a half plus 1. That's the antiderivative that we will simplify later on. I drop the c because I have definite integral. And then this whole thing will be evaluated between 1 and 9. Means I find the value at 9 minus the value at 1. Now the rest should not be difficult anymore. A half plus 1 is 3/2, property of fraction, 2/3, x to the power 3/2, minus a half plus 1, that's a half, property of fraction, 2, x to the power a half, and the whole thing between 1 and 9. So finally, this is equal to, I evaluate at the upper minus the lower. means. So the whole thing at the upper limit. 2/3, 9 to the 3/2 minus 2, 9 to the half, minus 1 is 2/3 minus 2 because it's just 1. So finally, I will get, now let's see, 9 to the power 3/2, it's basically how much? 9 to the half is a 3, that's a 27, minus square root of 9 is 3, so that's a 6. And then 2/3 minus 1, minus 2. Okay, and then you do the math. I think I am done. You get, I think, 40/3, end of the problem. All right? Questions?
So is this the like most accurate way to
As the
find?
most, yes. As if you know the antiderivative, that's the crucial idea. If we know the antiderivative, the fundamental theorem of calculus is the way to go. Okay, if you don't know the antiderivative, or I mean we haven't learned it, or there is no way we can find an easy way, and then the way definite integral is computed is actually by Riemann sum. Actually, your calculator compute definite integral, as you guys know, and you have all those computer algebra system, they do it. And the way they do it is actually, they have a fast algorithm to evaluate Riemann sum. That's how they do it. They don't use the fundamental theorem. They have a very fast way. They have, fantastic algorithm, but it's based on the idea of Riemann sum. But for us in this class, and in a lot of your courses, when you're going to find a definite integral, most of the time you will be dealing with function where we know the antiderivative. And then you will be using the fundamental theorem of calculus. Now, definite integral and substitution. So we know that one way to find antiderivative is using substitution. So if we have a definite integral and we need to use substitution to evaluate the antiderivative, how do we deal with that? So definite integral and substitution. Okay, so let us say when we need substitution to find definite integral, we can do the problem in two slightly different ways. So one method, so we have two methods to do that. One method is, suppose I want to evaluate this integral, a typical substitution problem. Okay. One method is, we need the antiderivative. So I forget about 0,4. I go after my antiderivative. Once I find it, I apply the fundamental theorem of calculus verbatim. So the first method. Find antiderivative of the integrand, then use the fundamental theorem of calculus verbatim, the way we do it. So first I need to focus on the antiderivative. So for a little bit, I'm gonna forget the limit because I want the antiderivative. So let's look for it. So now I'm only after the antiderivative because that's what I need. So let us remember how do we find the antiderivative. That's the substitution. So I'm going to put u to be 2x plus 1 because I have an inside function. The du is the derivative of 2x plus 1, which is a 2 du. And now I do the substitution, give me equal to. So now that's the antiderivative. This will become the square root of u. Dx, I don't have it. Oh, my apology. I don't have dx here. I want to substitute dx in terms of du. So I have to divide by 2 here to be able to do that. And then the dx would become a half du. And this would be a half. I can take it out. And this would be the square root of u du. Okay, mind you, I'm still working to find the antiderivative. So first I'm finding the antiderivative. That's equal to. Now I have an integral in u alone. I evaluate as an integral in u. And u to the half, we've done it basically several times. It will give me the 2/3 u to the power 3/2. And I'm not going to put c because I know eventually I have a definite integral. So I don't really have to worry about it. 2 and 2 simplify. So I will end up with 1/3. And then I need the antiderivative of this. That's a function of x. So I go back to my x, to x plus 1 to the power 3/2. So far I only did, I found the antiderivative. Now I imply the fundamental theorem, verbatim. So this would give me, this is equal to the antiderivative evaluated between 0 and 4. Okay, so now I evaluate between 0 and 4. So this would give me everything at 4 minus at 0. All right, at 4 I will get 1/3 times 2 times 4, 8, 8 plus 1, 9 to the power 3/2 minus 1/3, and at 0 I will have 1 to the power 3/2. So finally I will have 1/3 times 9 to the power 3/2 is a 27 minus 1/3. Okay, and this will give me 26/3 or whatever, 26/3 it is. No, I cannot do anything about it. 26/3. All right. So the first method to do this is nothing really new. I need an antiderivative. I forget about limit for a little bit. I found the antiderivative by regular substitution. And once I am done with it, I go back to my definite integral. That's the antiderivative. I evaluate it between 0 and 4 because those are my upper and lower limit, and then I do the work. All right. The second approach is the following. The second approach is the same thing with a slight change. We're gonna not only do a substitution for what's inside, but we're also gonna substitute the limit in terms of u. So let me see. So the second method is basically to change the limit of integration at the beginning. Change the limit of integration when the variable is changed and never go back to x. And let's see what I am talking about. Okay,
Professor?
Yes, I'm listening.
Okay. Could you go back to that last answer? My answer was different. I got 9.
Got 9. Okay,
Yes.
I usually do stupid mistakes. Where did you lose me?
You did the 1/3 times 9 to the 3/2 power, correct?
Yeah, this is 27, right?
Yes.
Okay.
And then 1/3 of 27 is 9, I think. That's what I have in my calculator.
Yeah, but then you forgot that
Okay.
you forgot this piece.
Right. Okay.
Okay.
Yep.
Okay.
Thank you.
Yeah, student a lot of time forget this piece. So I'm glad you mentioned it. Very good. Now, so the second method is to change the limit of integration when the variable is changed. What I am talking about. So I'm going to go back to the same problem. I'm going to evaluate this. Okay. The approach is the same. I need substitution to find the antiderivative. That's the piece I will not really change it. So we need the substitution. So we're going to put u to be to x plus 1. And the du is 2 dx. And we need the half du by looking carefully, which is giving the dx. But this time, when I'm going to change a new variable. I'm also going to change the limit. So right here, what I'm going to change, actually, I'm going to write it here too. So we will change the limit. We're going to also change the limit of integration. What do I mean by that? It means when x is 0, my u will become 2 times 0 plus 1, which is 1. So I'm going to also say, okay, if x is 0, what will be my new u? And then if x is 4, what is my u? I substitute 4 for x here. This gives me a 9. And now, of course, that is based on a formula that I'm using. Then the integral from 0 to 4 of the square root of 2x plus 1 dx will become the following. I want to change this time. It's a definite integral. It will become integral from the 0, when x is 0, u is 1. So this is going to change to 1. When x is 4, u is 9. So this we will change it to 9. Everything in terms of u, also the limit, are going to be changed. The square root of 2x plus 1 is the square root of u. The dx is a half du. Okay. Now, when I change the limit of integration, at this stage, I evaluate this new integral in u with the new limit. And I don't go back to the initial limit in x anymore. So if I do change the limit of integration from 0,4 to 1,9, then I don't go back to x anymore. It means I evaluate this new definite integral with the new limit, and I am done. Okay, so what do I mean by that? So it's going to be equal to a half times the integral from 1 to 9 of the square root of u du. Means equal to a half times. Antiderivative of that is 2/3 u to the power 3/2. Why? Because we've done it several times, between 1 and 9. Notice I'm not going back to x anymore. I'm not. So finally, this is equal to. So now I have an integral in u with a new limit times 2/3 9 to the power 3/2 minus 2/3 1 to the power 3/2. And finally, I get a half times 9 to the. I'm listening.
Why don't we just multiply the 1/2 times the 2/3 like we did in the last one, or no?
Yeah, I will mention it in a second. Give me 1 minute.
Okay.
You're fine.
All right.
You're absolutely correct. Give me a minute. Yeah, it's
All
a good question. 2/3 times 27 minus 2/3. And then I am done. Basically, I will have a half times 2/3 times 27 minus 2/3. So we can simplify. So if you want, this is 9. Give me 18 minus 2/3. And if I do the math correctly, I will get 26/3. Okay. Now I will go back to your classmate's question. Okay. Oh, I will explain it tomorrow, Eli. Yeah, it's not a big deal. Okay. Yeah, that's a good question. Yeah. Now this is equal to. Let's see, it's equal to that. This is, your classmate was telling me the following. Can I pull the 2/3? And he's absolutely correct. We can pull the 2/3 because the 2/3 is part of here and it's here, well, which will mathematically will be way easier. So it will be easier if you want, pull the 2/3 and then you will have 9 to the 3/2 minus 1. And that's mathematically, it's actually even easier. And that's what give me 1/3 times 27 minus 1, which is equal to 6. All right, and that's actually even easier. So the idea is that if you have like 2/3 times u to the 3/2 between 1 and 9, you can actually pull the 2/3 out. Why you can pull 2/3 out? Because as you see it, when I substitute, I'll have the 2/3 here and the 2/3 here. So actually this 2/3, this constant, can be pulled outside. So in other words, at this stage, I could have done that. I could have said this is a half times 2/3 times u to the 3/2 between 1 and 9. It means this piece, this constant, could be pulled out. and then evaluate only this function between 9 and 1 because of this reason right there. Right, I definitely have to stop, finish your review for tomorrow, and I will try to answer your classmate question, why this worked. It's not actually, it's not very hard. I will try to explain it tomorrow. A little bit hard, but not too much. And what else? And remember, tomorrow is your first quiz, and it will cover everything I did so far. I mean, all the review I went over, that it will be covered on your quiz tomorrow. And I guess, do you have any questions?
The quizzes are all on math lab, correct?
No. The quiz is written. You guys will have to write stuff. Okay. So the quiz would be, I will put the quiz on Brightspace. Okay, tomorrow. And then you guys will have to write it very neatly on a nice piece of paper and then upload it. Okay. Whoever answered me asked the question, do you understand?
Yes, thank you.
We'll do that. Yeah, you have to write, not on my lab. I need to see you writing. I need to see you writing the limit of the Riemann sum. I have to see that. I want to make sure you guys can do those ideas. All right. So make sure you finish the review for tomorrow. Bye-bye, guys.
All right, have a good day.
Goodbye.